Okay, streaming's on, website's up. This was from the other, the Monday, Wednesday assembly programming class. We were just talking about some stuff, and Java came up, okay, and then we started to talk about how Java was used in one of the Mars rovers. It was the Spirit. The Mars rover Spirit was using, Java as its basic, engine software part. So that was kind of interesting. All right, so for this class, we have a new homework assignment. Probably the last one, because this one is due all the way at the end of the semester. So you have 2 weeks to work on this one, which also means it's probably a little bit more involved than your other homework assignments. It's called new instruction. So let's take a look at the homework assignment. First, we'll look at the description of the homework assignment, and then we'll kind of investigate how to get it done. Are there any questions at this point? I do have your test that I can hand back. It's not graded yet, but I have scanned everything. So, I would just work off the scanned version. So if you guys want the test back, it's all cool. I'm going to pass it only from one side. So this way people don't get confused, because I start from both sides. There you go. Take it on this side. There are no markings on it. So there are no points, no marking whatsoever. So if you just kind of pick your own, it should be okay. Okay, so getting back to the new homework assignment. So in this homework assignment, we're implementing a new instruction. Okay, so it resembles one of the questions in the earlier final exams. Okay, but this one is an actual homework assignment. You got 2 weeks to do it. And what we want to do is, I want to be able to use a new instruction so that D points to a memory location in RAM. Whatever is in that location, the content of that RAM location will be used to update the flags register. The flags register is where you store the carry flag, the zero flag, the borrow flag. I mean, that's the carry, but the sign overflow and the L flag. Okay. So I want to be able to, just load it, okay? This is for loading, because the other class is doing the storing. So this class is doing the loading. So this will require a change to the architecture, because currently there's no pathway between the input port of the flags register and the data port of RAM. So there's no connectivity right now. This pathway cannot be a direct connection because RAM is shared with many other components. So you cannot just say, okay, we'll just make a connection from here to here. A further requirement of this assignment is to make sure that there's no change to existing instructions nor their microcode slices. So I don't want to have to change the ROM. I don't want to change the individual locations in ROM. I just want to add this instruction with backward compatibility. Is that okay? So all existing programs that are assembled should continue to work as they were. But we're adding this new instruction. The opcode, the mnemonic of the instruction is LDF, which stands for load flag, and then the opcode is 47 in hexadecimal. So your job is to update the entire tool chain to implement this instruction. Okay? So are there any questions about this part up to here? What do you mean by the tool chain, right? I mean, that's the first question is, what do you mean by the entire tool chain? Okay, so let me see if I can bring up my tablet here. It's kind of what you use, the entire tool chain refers to what you use in order to do your homework assignment, your previous homework assignment. But it may also involve a little bit more than that. So it kind of depends on how you want to do it. Oh, great, it does show up this time. Sometimes, some days it doesn't show up. I can actually make a connection, but I cannot, the screen on the device does not show up on the PC. But the other way around works. I can actually control it. Okay, so the first question is, what is the entire tool chain? So let's say you write a program in assembly, for the toy processor. What is the next thing that you do? You put it into the the assembler, the spreadsheet, right? Okay, so as far as the tool, oh, okay, wrong color. Okay, so as far as the tool chain is concerned, the first one is your assembler, which is a Google Sheet. Google Sheet. There we go. And then what do? So let's say the assembler says, okay, there are no syntax error whatsoever, and then it gives you a what? CSV file. It gives you a CSV file. Okay, so
RAM.
The RAM for RAM. Okay, so you load it into RAM. Okay, so now we move on to LogicSim. So inside LogicSim, what is specific to the toy processor? The architecture itself, obviously, but there's also one piece that is really kind of important. I can give you the architecture, but if I don't give you the content of the ROM, the whole thing is useless, right? So the ROM content is the next one, okay? So the ROM content, which is your microcode slices, right? Microcode slices. Okay, so that's basically the minimum tool chain that we are talking about. So as we go along, I will show you options of doing things. For those of you who like to fully automate everything, you can change my opcodes tool chain so that you can regenerate the ROM autonomously, or not so much autonomously, but it's quicker to do it that way. For those of you who don't want to mess around with my code and just say, okay, I can do all the bit fields and then I can convert everything into hexadecimal, you can do it that way too. You can just change the ROM itself and solve that problem. So there are different ways of solving the problem. Okay, so the LogicSim consists of both the ROM and the processor architecture itself. So there are two pieces to it. All right, is that okay? So I'm going to do a few pieces for you. Okay, namely, I'm going to do the tool chain side on the assembler. So I'm going to go to the assembler here and kind of show you how you can add an instruction relatively quickly. So what we do, what I do, okay, you don't have to do this, okay, just remember I'm doing this for you already. So whenever I need to implement a new instruction, I just add to this table here. So in this case, the mnemonic of the new instruction is LDF, so I just add LDF here. And it warns because I set this sheet up to be protected. So every time I update it, it will say, okay, are you sure you want to update it? Okay, the opcode is 47, okay? And that's it, because this particular instruction does not take any operands. It does not need you to specify which register, or immediate values. There's none of those. So we're done here, okay? All of the other columns, from column C all the way to column I, those are only useful when you need to specify register XX, register YY, or an immediate value like I, okay? But this instruction is self-contained. It doesn't do anything. It doesn't need anything else. So are we doing okay so far with this stuff up to this point? So I'm doing this part for you. Yep, go ahead.
How does it specify the address? It's all
The address
of RAM.
Because it is implicitly using register D as to do the dereferencing. So that's why it is not a part of the instruction. It just knows that it has to use register D, because register D is kind of special because we use it as a stack pointer, by standard, by convention. So that's why we are now moving into what we call special purpose registers. Register D is now a special purpose register because certain instructions only apply to register D, but not any of the other registers. Okay, so this is all done. We have to check it. So I'm going to change the first instruction from STF, from the previous class, to LDF. So first of all, I double check and make sure there's no error message here, which means the assembler correctly recognized LDF as a correct mnemonic. And then we go to the output, and it does crank out the code of 47 in hexadecimal. So the assembler part is done, okay? You don't have to worry about this part. So, but if you already have downloaded the browser before, you will have to re-download it because this is updated now. So when you test your code, you have to use the new version of the assembler. Okay, so getting back to the assignment, let's see, where am I here? No, this is the other one. Yep, this is the one. Okay, so we do some editing because I'm done with certain parts already. So I'm gonna mark this part is not done, but the assembler is done. So there's nothing to turn in. Okay, so you don't have to turn in the assembler spreadsheet because, hey, you know, otherwise you will all be turning in a copy of mine, right? So there's no point in doing that. Okay, so the next one is going to be the actual meat of the project, which is how do you change the schematic to get this done? Okay, so for this, I'm going to use my not document camera, but okay, let's see, can I import from here? Yep, okay. So I'm going to import from the processor PDF again. So we go to do we have the I'm looking for the PDF. It might be in processor shared. Yep, it's right here. Oh, okay, it doesn't like that. Okay, making it 1, or better yet, LDF. There we go. Okay, so we are looking at the current existing processor architecture. I'm going to zoom in. Okay, I have to enable that first. Zoom. There we go. There we go. All right, so the flags register is right here. This is your flags register. The left-hand side is the input. Okay, so let me highlight here which part I'm talking about. Okay, so this is the input. This is what we call the D port of your register. So right now it only connects to the ALU. So when you track down this wire, okay, this wire goes around here and then go back here, and it connects to flags out from the ALU. So right away we have a little bit of a problem because conceptually what we want to do is to connect this point, the D port of the flags register, to the D port of RAM. So where's D port of RAM? D port of RAM is right here. So let me track it down for you. So we draw a green line to track this down. And it does split, you know, into a few places. So right here it splits into this part. It goes in this direction, and also this part that goes in this direction. Can you guys see the green highlight? Is that okay? Sort of. Okay. So this wire, the top one, goes all the way here, and then it splits again. In other words, it can potentially feed into the input of the register bank, but it can also potentially feed into the program counter. In other words, the output of RAM, the data port of RAM, can be used to update a few components. And I'm going to highlight those components because you're going to need to know which ones can potentially be updated by the data port of RAM. One is the program counter. The other one is the input of the register bank, okay? And there's one more. So when you track down, okay, when you track down this wire, okay, it goes down here too. And it can also potentially update the instruction register. Now the reason why you have to understand, you know, what can potentially be updated from the data bus is to make sure that when you update the flags register, none of those other things are getting updated, and vice versa. Is that okay? So you have to derive some kind of an equation to say that, okay, this equation, okay, when it is true, it means the flags register needs to be updated, and none of the other ones should be updated. But then we also have another problem, because right now the flags register, okay, if you track down this green wire, it is going straight into the output, the flags output of the ALU. So this means that you cannot just bridge it using a wire, okay? So I'm gonna put a wire here that is not gonna work. That wire is not gonna work. Okay, so if that wire is not gonna work, what do you need to do? Well, it looks to me that you are having two inputs that has to be selected in order to go into the flags register. Is that making any sense? Okay. So let me. So the first thing you need to do is to break one of the connections. And I'm going to use an eraser to illustrate it. This connection here probably has to be erased like that. Okay, I'm also erasing some of the wires that I really should not be erasing because it's just an eraser tool. So this one stays, but the input of the flags register is now dangling, right? It's not, there's nothing to specify, you know, what to use to update it. So what you need is something that looks like this, right? Where one side comes from RAM, the other side comes from the ALU, and then whatever this output is what you connect to the D port of the register. That is the modification that you need to make, just in terms of, you know, which component you're adding to the whole thing. Is that making any sense so far? Sort of? Okay. And how do we call this component here? It is called a multiplexer. Exactly. It has multiple input, one single output, and then you have a selection bit, in this case, to say, okay, which input should I use to connect to the output? Okay. Output enable is probably not needed. In other words, you can keep it can always drive, but it has to select which input it is using to update the output. Is that okay? So the next big question is the selection pin coming out of this thing here, okay, is now a question mark. What equation do you use in order to specify, oh, okay, you connect to the data bus or connect to flags out of the ALU? Is that okay? Yep.
Does this mean we go to the instruction having 4.7?
You
Once you put in the assembler as 4.7, that instruction we have to match it to the input selector.
You mean this question mark here?
Yeah.
The equation that you need to specify in the question mark is going to make the switch when you need to connect the data bus through the mux to the input of the register. So that becomes the tricky part, is, you know, when should it become a 1? Most of the time it should be 0. Okay, most of the time, well, okay, I should not say 0, but most of the time you should just continue to connect flags out through the mux and then go into the input of flags. But very occasionally, you know, just for the LDF instruction, it has to switch to the other input and say, okay, I'm taking whatever is on the data bus in order to update the flags register. Okay, so where do you get started with this? Well, first of all, you have to make sure that this doesn't get updated when it's not supposed to update from RAM. So what do you do? Well, there are several things you need to look at. When does it get updated? You know, when does the flag register get updated? Or how do you look, if you look at this schematic, how do you know when the flags register is getting updated? When is it enabled to be updated?
When the ALU has a value for that?
Not quite what I'm looking for, but I think you got the idea. Okay, but mechanically, what we do is we track down, you know, what is connecting to the enable. So I'm using a red wire here. We're tracking down this connection here. When that red wire, okay, let me use a thicker pen here. When this red wire is a 1, then the flags register can be updated. Does that make any sense? So this means you have to look at FC, which already has its own equation. So FC has its own equation already. It is when ALUEN is a, okay, let me check here. When ALUEN is a 1 and register output 1 demux is also a 1, then the output is going to be a 0. But when the output is 0, it's now negated into a 1. That is when the flags register is going to be updated. So you might need to change that as well. Because now we have to say, but sometimes when we want to update the flags register, we are not doing anything with the ALU. We just want to read it from RAM.
A direct path from FC.
Huh?
A direct path from FC to
A direct path. So FC needs to be changed. This equation here, this whole equation might need to be changed. When you enable the flags register, needs to be changed. Because the way it's set up right now is we update when the ALUEN flag is a 1, register output 1 demux is a 1, then we update the flags register. So you need to change this equation and find out, okay, how do I change this so that we can have one additional trigger to turn on the enable of the flags register. Is that okay? Sort of? Maybe. Okay. Okay. So here's something that you can work with. Okay, you can kind of think about it this way. Okay, let me zoom out a little bit, and then change this back to fine and black. Okay. So what you need to do is to find out. Okay, first thing is find out. Okay, is it 2? Yep, it's 2 fine. Okay, find out what instructions relate to the flags register. Okay. Particularly which one is going to update it. Because we don't want to change it so that those instructions do not update the flags register anymore. Does that make any sense? So those would be your ALU type instructions: and, or, compare, subtract, not, and bit shift, right shift. So those are the instructions that will currently update the flags register. We want those instructions to continue to update the flag register. Okay, that's something we want them to continue to do. We also want to make sure that the other instructions, anything other than those instructions, will continue not to update the flags register. But this new instruction that we're adding, which is LDF, would also be updating the flags register. So the question now is, how do you change the FC equation to make that happen?
Looking for an answer? You could. My first thought would be you just OR the result of that negated AND that we saw that sets that enable pin.
Okay.
With something that is unique to the new opcode.
Yep.
But I haven't looked at which bits in that might be unique to only that.
Yep. So you will probably have to look at how I use the other bits at this point. Okay. So I'll give you one example of what potentially you can look into. Okay, let me go back to the picture here. Okay, so just to give you an example of what you can potentially use. Okay, do you guys remember what I said about when? Okay, for instance, okay, when register output and when register output 0 enable is a 0, typically we don't really care about what we specify as register output 0 select, because it doesn't matter. Okay, we are not using register output 0 at all. So why do we care which register we are selecting as the output 0 of the register bank? But you might need to hijack some of those bits in order to do something that we need to do for this particular instruction. Because we are not adding any additional bits in the ROM. Specifically just to say, okay, are we updating the flags register or not? So now you have to use existing bits, take a look at the existing microcode slices and go like, okay, what can we hijack in order to signify and go like, now update the flags register and use whatever you're reading from RAM to update it. Now when you update it from RAM, you got some clues already, because RAM select has to be a 1 and RAM load has to be a 1 as well. So that's giving you some clues already, like, okay, if RAM select is a 1, RAM load is a 1, that's also giving you a hint that we might want to update the flag register from RAM. But that by itself is not sufficient, because there are many other instructions that we turn on and say we're reading from RAM. So you need to differentiate LDF from LD itself. Okay? So getting back to the clue, or my hints here, okay? Look at or study, okay, the LD instruction itself, okay? And make sure we can differentiate between LD and LDF. Because LD is one of the few instructions that will say, okay, let's go to RAM and read something. LDF is also saying the same thing. Let's go to RAM and read something. But what they're reading into is different. One is reading directly into a register in the register bank. How do you know that it's reading into register bank, into one register in the register bank? If you look at the architecture, which bit tells you that we are dealing with LD but not LDF? Okay, let's magnify the register bank here. Which pin or which tunnel tells you that, yep, we're updating one of the registers in the register bank? Register input, yeah.
No, I was going to say RIN.
Yeah, RIN. Okay, so if RIN is a 0, but we are reading from RAM, that means we are not doing an LD. Is that making any sense? But do you want to use additional things to say that we are not reading from RAM into a register, but what else can it be reading into? I already circled those red things a little bit earlier. Because you also want to make sure that we are not accidentally updating the program counter. And the program counter is only going to be updated if PCEN is a 1. Is that making any sense? We also have another one that can update the instruction register, but the instruction register is not going to be updated unless the instruction register EN is a 1. So you have to make sure all of those things are 0s, because you don't want to accidentally update the flags register when the actual intention is really just to update one of the other registers. So are we doing okay so far with this? Okay. Let me go to the instruction part again. Okay. Track down what can be updated by RAM.D. That's the data port of RAM. So those would be all the other registers, and find out how each one is enabled. That is going to be important because you want to make sure that when you specify the opcode or the microcode for LDF, that it doesn't enable turn on any one of those other things. And vice versa, when you update any one of the other registers, you do not accidentally update the flags register either. Is that okay? More or less. Okay, so I'll get you guys starting to think about it because you do have 2 weeks to work on this one. So it's not like you have to get it done like within 2 days or even a week, but you have to start thinking about it. Okay, you have to start to look at the processor architecture as it is right now, and then think about, okay, how do we make sure that we do not accidentally update registers when we intend to update to something else. And the other thing is you might want to keep track of multiple versions of the processors and have one to start to have this modification in so that you can at least have the component already here. The multiplexer is already in, and then you're just having the big question mark here of saying, okay, how do we control the select of this multiplexer? Because that really is the big question. And then the other thing that you also need to study would be, well, not study so much as to understand, is how do we implement the other opcode? The microcode specification of all of the other opcodes is going to be significant as well. So that's also something that you need to kind of look into and go like, okay, so when we, okay, for instance, when we do a JMP, not JMP, a JMPI instruction, okay? A JMPI instruction will connect, okay, I'm gonna continue with the green line here and use a medium. So in that case, the data line will go through this mux here, go through this mux and update the program counter for the JMPI instruction or J blah blah I instruction. They all do this. So now the question is, how do you make sure that this does not trigger the update of the flags register? Is that okay or not? So that means you have to look into the microcode of the JMPI instruction and then go, okay, I cannot change that. I have to make sure that the microcode of the JMPI instruction does not accidentally update the flags register. Is that okay? How do you test your opcode? Let's say you figure it out and go like, okay, I can get this done in 2 days. How do you test it? This is going to be a bigger question, okay? It's a bigger question than doing the initial design itself, because now you have to double check and make sure that your implementation of the LDF instruction doesn't change the implementation of any existing instructions. How do you make sure that that is the case? Yep.
You could do a tracing of the program, see which ones get turned on.
Okay. So you can, okay, that's very good. Okay, in other words, what you're suggesting is we are going to trace all the existing instructions prior to the modification. We keep track of what each instruction is doing to everything inside the processor, and then we implement the new instruction. We run the same opcode again, and then we compare the actual traces and make sure that they are exactly the same. Yep. So how many instructions do you have to check?
Well, since there are the similarities, could you check all the J, like only one J, any B?
We have families of instructions.
Yeah.
Yep. Okay, so let's take a look at how we can get that to work. Okay. Okay. Okay, so how do we check the new opcode and make sure that it works the way it's supposed to? The first one is really just to check it. Okay, so just use the LDF instruction, initialize RAM location, and observe the update of the flags register. So to confirm this part is relatively easy, because all you have to do is to write a single program that has an LDF instruction followed by a halt instruction. Okay, you initialize a particular RAM location to be a particular value. You initialize register D to have a particular value. You run the program, and then you examine your flags register to see whether it has the content of that RAM location. If it does, everything is good. If not, the instruction is not working. So this is the easier part of the verification that your program works. But the bigger question is the change that you have made to the whole thing. How do you make sure that it doesn't interfere with the operation of the existing microcode slices of the existing opcodes? Now, if you're not changing the rest of the circuits, whatever the old instructions were doing, they will still keep doing. That's not a big problem. But how do you make sure that the existing opcode do not accidentally or erroneously also update the flags register when the flags register is not supposed to be updated? That becomes the bigger question. Okay, so I'm going to write it down here, okay? How to make sure existing opcodes do not accidentally update the flags register. That becomes a bigger question. So to answer this question, you can validate by testing the code, but that's going to be very tedious. The better way to do this is to kind of go back a little bit earlier and find out when you can have something that can be updated by the RAM data bus, what is the enabling mechanism? And make sure that those enabling mechanisms do not accidentally enable the flags registers enable. Okay? If you can prove that mathematically, then you don't have to test it, because you are just proving that with all of the other things that can be updated by RAM, when they're updating, we make sure that the flags register cannot be updated when those things are happening. So how do you make that happen? Okay, so let's take a quick look at what, for instance, okay, so we got IREN, that is the instruction register enable. We have PCEN, which is the program counter enable. So all of these things, they have to be a 1 in order to update the instruction register. There has to be a 1 to update the program counter, and so on, right? So now the question is, what kind of a gate do you put them into so that the output of this gate is going to be specifying, do not update the flags register. If at least one of these things is a 1, do not update the flags register. Now, I just said something that is kind of important, right? If at least one of these things is a 1, okay, so which gate or which logical operation comes to your mind?
And or.
There are only 2, right? Okay, so this is OR, okay, so OR. But then I also said, if at least one of these things is a 1, I do not want to update the flags register. So that means a negation, yep. So a NOR gate might be helpful. Is that okay so far? But you do have to remember that we have a negation also. FC goes through a negation before it goes into the EN of the flags register. So you're free to modify any component of the processor architecture as long as the ROM content does not need to be changed. So you can perform further modifications, things that I have not talked about today, to make it work. But I would just look into the minimal work to get it to work. Is that okay so far? So all of these are bits and pieces of what you need to do, and you kind of have to let it sink in a little bit and ask questions on Thursday, okay? You'll work on it a little bit, come back with questions on Thursday, and then we'll talk about it again on Thursday. But are we clear what we want to do? Okay. Okay, the next question, okay, this is, so you guys are you will be working on the nitty-gritty detail of the homework assignment, which is the how, okay? What is already described by the homework assignment, but what I did not tell you was the why. Why are we doing this?
Because you told us to.
Because it's fun, right? Okay, so the pair of instruction, which is STF load flag, and STF, okay, which is the matching instruction. So when you look at the C code, load F is the same thing as flags, FLAGS, equals to dereference the D register. The other one is the opposite, dereference the D register and update whatever RAM location D points to with a flags register. But why is this important?
Oh,
It-
you want the Boolean there?
I want to be able to save this flags register and then restore it at a later point. But why do I want to do that?
Maybe for recursive.
For recursion or subroutine call, right? Any kind of subroutine calls. Because in addition to having register A, B, and C, basically clobbered or updated or modified by the subroutine, the flags register is also not guaranteed to be the same when it returns from a subroutine. What if it is important to you as a caller? So you do some comparison, you do some complicated stuff, and you say, okay, this flags register is really important to me. Okay, I need to remember whether the Z flag is on, or whether the carry flag is on, whether the L flag is on. But it's time for me to call a subroutine at this point, but I need that information back later on. Well, the current architecture has no way to do it. But with this, okay, now this doesn't seem like much, but with this, I can do it now. Okay, so the idea is to do something like this. So from the caller's code, okay, this is the caller's side of code. You do some, okay, complex operation to update the flags register. Okay, so at some point the flags register is really useful and you don't want to lose it. But it's time for you to call a subroutine. So for whatever reason, it's time to call a subroutine. So here's the call of a subroutine. Call, subroutine. But you want to preserve the flags register. So now with the added instructions, how do you preserve the flags register? Well, we have STF, which stores the flag register to where the register D is pointing to. Wait, register D has a special purpose. What is it? It's our stack pointer, okay? Okay, cool. So that means at this point, if I do a decrement D, I'm allocating a byte on the stack, right? And then all I need to do is to do STF. So this way, I am storing the flags register directly to the new location on the stack that I have allocated. Now I call the subroutine using those 5 or 6 lines to call a subroutine, set up all the parameters, whatever. Okay. When the subroutine returns, okay, and then I go like, okay, at some point later on, I say, okay, I want to retrieve the flags register so I can perform some conditional branches. Guess what? Now we can do LDF, increment D to deallocate that byte. So these two is for saving the flags register, and these two are for restoring the flags register. So they are very handy this way. Is that okay? Because without this, to save the actual flags register is a difficult thing. Now this comes in even more handy. Now, because in this case, you do have control. Okay, when you're calling something. Okay, I'm gonna use a red pen over here because this operation is what we call synchronous. It's synchronous. The term synchronous in this case refers to the fact that the caller, okay, whatever this code is, has complete control over when to call a subroutine. In other words, if this is not a good time to call the subroutine, do it some other time. Okay, utilize the flags register first, then call the subroutine. Or go to a particular place so that you can use the branch to indicate the status of the flags register so that you don't have to restore the flags register. So being synchronous has this advantage. Do you guys remember that we talked about interrupts? So what is interrupt? What are interrupts? It's kind of like calling a subroutine, except for one thing. What is the one difference between calling a subroutine in software versus an interrupt happening? Okay, so let's use some code over here. So let's just say that we have an LDI instruction, LDIA with 0. Okay, I cannot do a hexadecimal in the assembler, so we'll just call 23, LDIB with 62, and then we can do a jump instruction. Then we can do the call stuff, okay, which is decrement D, LDI A with, let's do C here. Return address 1, STDC, and then we do LD. I don't think we need another LDI. So now we can do a JMPI to sub 1, and then here's return address 1. Okay, so in this particular code, this is the whole sequence to call a subroutine, right? Okay, and you have complete control over that. So versus the alternative, which is, okay, so we have LDI A23, LDI, okay, I'm just looking at the code here, 62, B with 62, and let's just say that we have LDI C with 36 over here. If you have interrupts, or if the processor supports interrupts, when do you think the interrupt is going to come in? First of all, what is the interrupt? Who's causing the interrupt? What can potentially be causing the interrupt? Well, it depends on what you're using the processor for, right? So in the case of a real desktop computer, what kind of event, what kind of things that you do can potentially trigger a hardware interrupt? In other words, the processor and the operating system is just doing its own thing, and then suddenly somebody says, hey, processor, we need your attention to do something. So what do you think would be the cause of that?
Starting a program?
Well, okay, that's very good. But when you start a program, what user interaction will eventually cause the starting of a program? Okay, so tell me how you interact with your computers. You have to click on something. Okay, very good. Okay, you have to click on something, and when you move your mouse, what do you think happens to the computer? As you move the mouse physically, okay, like this. Okay, what do you think happens? How does the computer know that, oh, the mouse just moved? We better update the pointer on the screen. Interrupts. Okay, very good. Okay, good. Okay. So every time you type something on the keyboard, every time you click a button, every time you move the mouse, okay, it generates a sequence of interrupts, not just one, a whole bunch of interrupts. Because every single event of a device, like a mouse or keyboard, generates an interrupt. An interrupt, in this case, if I move the mouse, okay, the interrupt is telling the processor, okay, through the USB controller and stuff like that. But eventually, it is telling the processor and say, oh, I have just moved to the right-hand side by 20 pixels, and I've moved up by 6 pixels. That is the communication between the mouse and your main processor and the main computer. Okay? But it's an interrupt because it doesn't make any sense for the operating system to keep asking the mouse and say, hey, did you get an update? Did you get an update? Did you get an update? Well, because if you ask a mouse that question, you have to ask the same question to the keyboard. You have to ask the same question to the network controller. You have to ask the same question to the sound card, okay, for the microphone, right? So you have to ask the same question to just about every device in your computer. It doesn't make any sense. Polling doesn't make sense. So instead, what the processor or what the operating system is going to do is to say, I will keep doing what I'm usually doing, okay, do some background processing, sleeping, okay, being in a low energy state or low energy consumption state. When your mouse does move, okay, it causes an actual hardware event, okay, electronically to the processor and say, hey, I need some attention. And at that point, the processor, even if it's doing something that's useful, like doing some execution, do some calculation and whatnot, it would just say, okay, I'm gonna put this on hold. I'm going to process this interrupt and see who needs my attention, and then come back and do this later. Does that make any sense? So what do you think the processor is gonna do when the interrupt happens? So I'm going to go back to this slide here. So let's say you're right between the execution of these two instructions, with a toy processor. Let's just say it hooks up to a button. Okay, we just want to know whether somebody is clicking that button or not. So let's say between the time between these two instructions, somebody clicked the button. An interrupt will happen. Okay, if the toy processor supports interrupts, then an interrupt can happen between these two instructions. And then what do you think would happen when an interrupt happens? Remember what it needs to do. It needs to go into what we call an ISR, or interrupt surface routine, do whatever code is over there, okay, which is also written in TTP-ASM. When it's done, it will come back to this point and continue execution with the LDI C36 instruction. What does that sound like to you? It sounds like a function call. Very good. Okay, so it is more or less a hardware function call, but it goes through the same mechanism as a regular function call. In other words, it has to find out what the program counter is at this point. Remember that on the stack, and then it will continue execution in the ISR, the interrupt surface routine. So the interrupt surface routine has something to do. Okay, so. So the interrupt happening here, it will go through a few things. I'm going to use different colors here to indicate which part is done in hardware and which part is done in software. The blue part is done in hardware. Okay, so what the hardware is going to do is it will do a decrement D, and then it will do a ST. Okay, we don't have instructions to do this, but in register transfer mode, okay, I'm going to change this a little bit here. We'll decrement D, and then whatever D points to is going to be storing the program counter. Okay, and then we'll switch back to the software, and then it will continue execution at the interrupt surface routine. So the PC equals to ISR address. Okay, so it will directly continue execution over at the ISR address. And then we'll switch back to software. In other words, now we're switching back to the software that you specified in the ISR. So now you're at the ISR ADDR, okay, which looks just like a subroutine. But from the perspective of your program, the program that is getting interrupted, you don't want to mess around with register A or register B, or register C if it was already initialized, right? But what can you possibly do when somebody tells you, hey, you're not supposed to touch any of the registers?
You start the registers.
Well, you can either do nothing because you can't do anything, or you can say, I'm going to save all the registers. and then we'll go ahead and do things, right? Okay, saving the registers is not a big deal. We know how to do that, okay? Because all you have to do is to do a decrement D, then go like, oh, but we're changing the stack pointer. Well, the stack pointer is easy to deal with because you just have to make sure we have the same number of increments to get it back to where it started off with. So we don't have a problem with decrementing the stack pointer. Then you can do a stda, okay, to save register A. Okay, decrement D, stdb, decrement D, stdc, and those are all the registers that we have to save. Then you can perform whatever calculation, whatever operation that you need to do in order to say, okay, when somebody clicks this button, I'm going to turn on that LED over there. But somewhere along this line, you might have compare instructions. You might have add instructions. You might have subtract instructions. And they will change the flags register. Right? But is that a good thing or a bad thing? It's a bad thing because whatever code you're interrupting may be right between a compare and a conditional branch. Okay? So if your interrupt surface routine is changing the flags register without restoring it, then we have a problem. So that is why the STF and the LDF instructions are also useful in the context of an ISR, because now you can say, oh, we also need to save the flags register. So you have a decrement D again, STF to store the flags register. It doesn't need D as an operand because it is implicit. I decided not to make this general purpose. In other words, I decided not to specify that you can store the flags register into whatever A points to, into whatever B points to, into whatever C points to, and so on, because most likely you just need to store it to whatever D points to. So that's the only reason why I did not make this a general instruction, because it's going to take up 4 opcodes if I make it general, but it's going to only take up 1 opcode if I specify it. Go, okay, it only goes to where D points to. So this way I have more opcodes left to implement other useful instructions. Okay, so at this point, now you can really do anything you want to. You can use register A, B, C, you can change the flags register. In other words, you can compare, you can add, you can do whatever you want. At the very end here, then you have to restore everything. So to restore everything, you start with the LDF instruction, and then you increment D, okay, and then you reverse all the other operations, which is LD, in this case C from D, increment again, LD B from D, increment again, LD A from D, and then at this point you have to do a return. The usual way that we do a return is not going to work anymore. Right? Because the way we usually do a return requires the clobbering or updating of a register. So we need another special instruction here to do the return without using one of the registers. Guess what? That was one of the questions in exam 2. Do you guys remember that one? And that one did not require a change to the architecture because we got the right pathways already. We just did not have those instructions in the same thing. So I'm going to put a blue thing here because it is done already, but we don't have the actual opcode to do it. So in here, we basically just have a PC equals to whatever the D register is pointing to, but we also have a post increment at the same time. But that blue thing at the very end, we can do that without modification of the architecture already. But the assembler doesn't implement that instruction yet. So we do okay so far with this? Maybe. So I'm just trying to explain the rationale behind why we want to implement the LDF and the STF instruction. We're setting up the toy processor to be able to deal with interrupts. You can imagine the joy of some students in the next semester. But that's kind of like a growing project. You know, every semester we do some tweaks to it. We add some instructions. We expand what the processor can do, and in the process, you know, we kind of hopefully gain more understanding of what happens inside the processor. Is that okay so far? Okay. And what kind of processor do you think, you know, can deal with interrupts? In terms of, you know, like how expensive of a processor, you know, how much processing speed it has, that sort of thing.
Pretty much any modern processor.
Just about any modern processor. From what price range? What do you think would be the price range that we are talking about here?
$5.
$5.
$35.
Yeah.
Okay, $35. Okay, I'll take your $35.
10 or 15.
Okay, so there's this is the one that I'm really familiar with, but it's definitely not the only one. These are all called microcontrollers. So basically, a microcontroller is a self-contained silicon chip that combines the processor, ROM for the program itself, RAM for variables and the stack, and input-output peripherals onto a single chip. So you might think, oh, that's going to be a pretty big chip. Well, no, it's tiny. Okay, and therefore the name ATtiny. So we'll take a look at one of these. Okay, so we'll take, this is a really great website if you're into this sort of thing. Number of input outputs, you know, we'll specify the minimum. Actually, I'm going to clear this. Let's take a look at how much program RAM memory it has. 256 by 16. Which means it has 256 locations, and each location is 16-bit wide, which also means we can only have up to 256 opcodes. How do you write a program with only 256 opcodes? But the toy processor is kind of in the same boat, right? How much RAM does it have? 32 by 8. Well, that's actually cheating because it has 32 general purpose registers. They're counting registers as RAM in that case. Okay, so let's pick out this one here. This part specifies, you know, with what voltage it can run and stuff like that. So we're gonna submit this. Okay, apply filters. See what we have left here. Okay, running at 10 megahertz. Yes, you read it right. It's not gigahertz, it's megahertz. It's 10 megahertz. So we'll pick this one. We'll pick apply filter again. And then we only got program size. You know, we got, let's pick the bigger one and see. Okay, let's make it active. And we have 12 choices left. Okay. The packaging part has to do with how many you're buying. If you're buying cut tape, you know, you're buying like small quantities from 1 to, I guess, you know, maybe a few tens. If you want to buy hundreds of thousands, you have to buy the reel type, because, you know, it comes in a reel, okay, like a big snail shell thing. And the reason why it comes in the reel is people put these things into what we call pick and place machines. How do you think PC printed circuit boards are assembled? Okay, your printed circuit board, which is an FR4 type of thing, it's got copper and pads on both sides, right? Sometimes on only one side, and you need to have components put onto it, and then, you know, solder and stuff like that, right? So how do you think that is assembled? Yep.
I kind of saw a process of this. They're put on the table,
Okay.
a bunch of them, and then they have a machine just solder.
Okay, but before you solder it, you have to have the components on it first, right? Okay, so so first of all, when you look at a PC printed circuit board, like an Arduino, it's only about this big, right? They do not do it per circuit board. So what they do is they come in a sheet. So the circuit board, it comes in a sheet which is about this big. So it's tiled with many you know, Arduino boards already tiled onto one big sheet. And then what they do is they put a stencil on top of the whole thing, okay, which is kind of like a metallic film with openings for the pads where the solder is supposed to go. So they put a stencil on the whole thing, and then they put solder paste onto the whole thing, and then they squeegee the whole thing. Okay? Then they remove the stencil. So once you remove the stencil, only the exposed places would have solder paste. Now solder paste is, right? Yeah, now is a good time. Right there. Rodney, do you want to do an introduction?
Oh, yeah, sure.
Yeah, go ahead. We're kind of at a good point to start anyway, so.
Okay.
Yeah, go ahead.
Hey everybody, my name is Rodney. I'm the internship developer and special projects coordinator for the Department of Business and Computer Science. What I do is I meet with companies and employers to offer internships and work experience opportunities just for our students here in BCS. So one thing that I've done is, since I'm out there in the community a lot, meeting with people, I ask different people who's at a high level saying, can you guys come in and speak to our classes regarding various things. So right now, I met David Mack. He works for AT&T, and him and I was engaged in a conversation a few months ago, and I said that I would love to have you come out and speak with our students. Your professor was so gracious enough to say it, absolutely. So I want to introduce David Mack from AT&T to do a little discussion.
Right, appreciate it. All right, thanks very much. All right. How's everybody doing today? All right, good. I appreciate Professor Ayang, right? Yep. Did I say it correctly? Good. Okay, all right, excellent. I'm on the right page now, I'm on the right path. I just wanted to take a few minutes, and again, I appreciate your time and allowing me to come in for a few minutes. I appreciate Mr. Flakes and the discussion that we had that actually put me here. So, there's a few things I'd like to kind of run by you, and the whole idea today is kind of to, give you a kind of a real world case on what's happening at AT&T, contrary to what you might know of the company, and to see how that might start you or turn you toward some things that you may either be interested in that you may not know about, or some things that may heighten the things that you're aware of. So before I do that, when I was talking to Mr. Flakes, and he finally had an opportunity to talk with the professor, and said, yeah, we're going to get you clear to come in. The first thing I thought was, okay, how can I make this kind of somewhat entertaining so that nobody falls asleep, right? Like, how many of us have been in those kind of classes, right? I mean, not this class, right? Right, not this class, okay? But it's my hope to give you some information to share with you that won't necessarily answer questions that you might have, but might start the questioning process for yourselves and your careers and your academic pursuits. So first, a little bit about me. You always try to figure how can I add credibility to what I'm about to tell you without dating myself. So I just figured, in order to just tell the story, I just have to date myself, right? So I'll just say it like this, okay? I've been in the high-tech, leading edge, bleeding edge technology game for 30 plus years, 30 years. Okay, it goes all the way back to when I was in college and I was selling computers. My background is mathematics and computer science. So I was selling computers in a Radio Shack. Nobody knows what Radio Shack. Like Radio Shack was a store that, Radio Shack probably, right? So Radio Shack, I was selling computers at a time when housing or your basic house did not have computers, and an idea of a computer was a good idea. So start thinking about how can I do word processing, how can I start doing spreadsheets, how can I do these type of things. So I was doing more of that, okay? Background computer science, and then I graduated from school, went on to take an offer from Microsoft, and I turned it down. I found that while I was selling computers, that I was better at working with people than I was writing code. I was okay, but I was never as good as being able to talk to people and help them use technology to solve business problems or to solve a problem. So I went to work for this very small software development company at that time that was doing bar-coded data acquisition systems. So, you know, you scan a barcode, you have some data that gets created, and now that data has to make something down the line do something, make a device do something, right? Print a barcode label or move a process forward or to create some type of further acquisition of data down the line, okay? So we were doing that in 89, 90, right? So how many of you guys were born in 89, 90? Oh my God, I'm in trouble. Okay, so in case this was at a time when none of this stuff was happening in the world, right? And we were doing these barcoded data collection systems in places like Argentina and Brazil and places where they didn't have running water or running toilets, but they had a warehouse that had RFDC, so radio frequency data collection systems where, you know, things were happening in a wireless environment, right? So from that, went on to work for GE and was, again, leading edge, bleeding edge, right? We were talking about these trucks that you see on the road every day, right? These big trucks with the big trailers on the back. Well, at that time, you know, they would always have to take a cell phone and call where they were, what they were doing, what's the next thing you're doing, how far is it going to be for you to get to your next location. We were building systems at GE that was, you know, software and back office data collection, where now, instead of relying on the driver to tell us what's going on, he's in the cab with a device, he presses a button, goes up to a GPS, goes down to a communication server, and now someone that's sitting in the office 2,000 miles away can look and see their truck with a little red dot on it. Now I don't have to rely on that guy. As long as he presses the buttons, I know the status of his load and where he's going and what he's doing next, or if he's late, or all that type of stuff, right? That was happening about 97, 98, okay? So worked for GE 5, 6 years, and then came to work for, which was then Pacific Bell, which then became SBC, which then became AT&T, right? So that's a story in and of itself, so I won't go into that. And that's where I've been the last, well, off and on 17 years. I've done some other things too. Started companies, I've started some chapter S corporations, operated them, sold them, and I even sit now as a chairman of a 501c3, which is a nonprofit organization, which is a charter school, right? It's actually a charter school. So I chair a school that's a K-8 school that's all about education. So you probably have figured it out by now. I love to talk about technology and I love to talk about stuff, right? So I don't see anybody falling asleep yet, so that's good. Okay. Okay, so what am I here to talk about? So here I'm here to, and by the way, if you have questions, feel free to raise your hand. Well, I'm going to get a little bit into the AT&T transformation, the business transformation that's taking place. But before I do that, before I tell you, I guess, about that, I want to kind of learn a little bit something about you guys. So if you're not shy, if you'd be kind to tell me so I can kind of steer what I want to talk about through your dreams. If I were to ask you the question, you know, say 10 years from now, which is for you probably 100 years from now, if in your wildest dreams, what would you be doing as far as your job? 10 years from now, if you could dream, what could you see yourself doing now, 10 years from now? Thoughts, ideas? Anybody dream? I'm sure we dream. Anybody got a dream?
I'll be teaching.
All right, Professor. That's a fantastic, okay? Any dream, any other dreams? Don't be shy. Yes, sir.
I guess working in artificial intelligence.
AI.
Yeah.
That is an excellent place to be. Because you probably discovered, just like some of the things I want to talk to you about today, that all of those things are in their very early infancy, right? I mean, if we're talking about, you know, the technology that we're aware of today, that's running like a relay race or a 100-meter race, AI is not even crawling yet as far as our potential and where it's going. So that's fantastic. Any other ideas or thoughts or dreams? Yes, sir.
Cybersecurity.
Cybersecurity. I'm going to hit that in a little bit. That is fantastic. Also something in its infancy, right? Everybody thinks that security is about protecting what you have. It's more than just protecting what you have, and I'll get into that in a little bit. That's fantastic. And by the way, there's everybody that I know that's in the cybersecurity game that's employed. Anybody have any idea to guess what the unemployment rate is for somebody working in cybersecurity? Take a wild guess.
Zero.
Zero, right? Zero. In fact, I'll talk for the company. Can't find enough educated, folks in the cybersecurity game that can go in and help customers, help clients understand the importance of what it is, right? I still talk to customers that say, companies, I won't disclose their names, but you'd be surprised, that they say, I say, tell me about your security policy. They say, we got a firewall, we got some patches, right? You're like, okay, so that just tells me that you have a lock on the door, but the windows are open, right? So we'll get into some of that today. Anybody else have a dream? Those are two very good ones, AI, cybersecurity. Yes, sir.
Mr. Mack, the person just informed me that this class, they have to leave, but all the students are going to lab.
Okay.
So we're going to continue this conversation in their lab.
Okay, excellent.
Okay, perfect.
That okay?
Yep.
Perfect.
So we are all moving to one to continue. Thank you.
Yes, sir.
I'll be over there as soon as I shut down here.